how a once impossible dream became a global engineering competition. Across laboratories in the United States, Europe, and Asia, engineers are working toward one of the most ambitious achievements in the history of science: building a practical nuclear fusion reactor. Fusion has been discussed for more than half a century, a technology always labeled as almost here, always just beyond reach. It was the promise of clean, abundant, stable energy, and the frustration of a breakthrough that never seemed to arrive. For decades, the question was simple: will fusion ever work outside of theory? Today, the tone has shifted. Not if, but when. And perhaps most importantly, who will get there first? In a surprising twist, the global race is no longer led exclusively by large government reactors. Instead, one of the strongest contenders is a private American company that believes it can deliver fusion electricity to the power grid within the next decade. This is the story of that race, and why the United States may be closer than ever to a technology that could reshape the next century. What nuclear fusion actually is. Fusion is often misunderstood because it shares a name with the nuclear power we already use, yet the two technologies are fundamentally different. Nuclear fission, used in today's reactors, splits heavy atoms like uranium. It works, but it produces long-lived radioactive waste and requires careful safety controls. Nuclear fusion, by contrast, fuses light atoms, usually isotopes of hydrogen, at temperatures exceeding 100 million degrees Celsius. When these atoms merge, they release extraordinary amounts of energy, with remarkably few byproducts. No long-lived radioactive waste, no carbon emissions, no risk of meltdown. Fuel derived from materials found in seawater, deuterium, tritium required, but breathable inside the reactor walls. A small fusion plant could theoretically power hundreds of thousands of homes using only a few kilograms of fuel per year. But these conditions create a new challenge. At such temperatures, matter becomes plasma, and plasma cannot touch any physical surface. It must be held in suspension by powerful magnetic fields inside a device known as a tokamak. This requirement has defined the last 60 years of fusion research, and it is the foundation of the race unfolding now. ITER, the original global hope. For decades, the world placed its expectations on a single enormous experiment, ITER, a multinational fusion facility in southern France. ITER is, funded by 35 nations, the largest fusion experiment ever constructed is designed to demonstrate sustained fusion reactions, expected to reach full experimental operation in the 2032 APIS. But ITER is not a power plant. Even when successful, it will not generate electricity. Its mission is scientific to prove physics at unprecedented scale. ITER's size, complexity, and international nature also mean long development timelines. And as the project slowed, a window opened for smaller, faster programs. That window was quickly filled largely by companies in the United States. A new American contender, Commonwealth Fusion Systems. In 2018, researchers from MIT's Plasma Science and Fusion Center founded Commonwealth Fusion Systems, or CFS. Their goal was not simply to advance the science, but to build a fusion reactor that could realistically power the grid. Their breakthrough came from a new material, Rebco high-temperature superconducting magnets. These magnets can generate magnetic fields far stronger than older superconductors, allowing tokamaks to shrink dramatically in size while maintaining or improving plasma confinement. Smaller reactors mean lower construction costs, faster iteration, fewer components and reduced engineering risk, easier commercial deployment resulted. In 2021, CFS demonstrated a full-scale 20 Tesla Rebco magnet, a milestone independently validated by experts and considered one of the most important advances in magnetic fusion in decades. It proved that compact, high-field fusion wasn't just theoretically possible, it was buildable. SPARC, the reactor that could redefine the race. Today, CFS is constructing SPARC, a compact tokamak in Devens, Massachusetts. SPARC aims to be the first fusion device to achieve net energy gain, operational as early as the late 2022s, a direct stepping stone to a power-producing reactor. Its site includes a full cryogenic cooling plant, high-power radiofrequency heating systems, precision plasma diagnostics, an operations center built like a small power station. If SPARC performs as predicted, it would be a turning point. the moment fusion shifts from scientific pursuit to commercial engineering reality. ARC, America's first commercial fusion plant? If SPARC succeeds, CFS plans to build ARC, its first commercial reactor. ARC is designed to produce roughly 400 megawatts of electricity, power around 150,000 homes, operate continuously without carbon emissions, require small quantities of hydrogen isotopes as fuel graze. Site selection is ongoing, with Virginia emerging as a leading candidate, though not formally finalized. Several tech companies, including Google, have already signed agreements to purchase ARC's future electricity. That kind of commitment to a not yet existing technology is rare, and signals strong confidence in the design. America's other fusion competitors. The U.S. private sector is now the most diverse fusion environment in the world. Helion Energy, Washington State, uses a linear, pulsed fusion system, claims it could deliver electricity by 2028, has a power purchase agreement with Microsoft Event. Ambitious timeline, but credible engineering progress. TE Technologies, California, developing a hydrogen boron fusion reactor. Fuel produces no neutron radiation, uses a field-reversed configuration instead of a tokamak. General Fusion, Canada and UK, backed by Jeff Bezos, pursuing magnetized target fusion using liquid metal liners once. These companies represent different pathways toward the same goal and create a competitive landscape unlike anything fusion has seen. China's expanding fusion program. China operates several advanced research reactors, including EAST, which has achieved world-leading plasma confinement durations. China is also developing next-generation superconducting magnets, large experimental tokamaks, fusion-fission hybrid concepts. While China has not yet focused on commercial rollout, its pace of development makes it a formidable participant in the global race. Why fusion matters right now. A global shift is underway. Electricity demand is rising sharply due to electric vehicles, industrial decarbonization, growth of AI and data centers, urbanization and population expansion. Renewables are scaling rapidly, but they are intermittent. Fission offers baseload power, but raises waste and political challenges. Fusion offers something unique, constant, 24/7 power, minimal long-term waste, no atmospheric emissions, a fuel supply that could last for millennia. Fusion would not replace other energy sources overnight, but over decades, it could reshape global grids and redefine energy security. What would it mean if fusion succeeds? The shift would be gradual, but profound. 1. Energy could become dramatically cheaper. A world with abundant electricity changes everything. Manufacturing, computing, transportation, desalination, agriculture. 2. Water scarcity could decline. Fusion-powered desalination plants could operate at massive scale. 3. Carbon emissions could fall permanently. Fusion is not a short-term climate fix but long-term. It changes trajectories. 4. Entirely new industries could emerge. Every era of energy transformation has triggered unexpected technological revolutions. 5. Geopolitics would shift. Energy security shapes global power structures. Fusion could redistribute that balance. Fusion will not solve every problem, but it expands the boundaries of what is possible. It gives humanity a larger horizon. Is America actually in the lead? Right now, the United States holds a unique position. The most private fusion startups in the world, billions in private funding Bing, the first high-field tokamak nearing operation dollars, multiple competing reactor designs, signed commercial power agreements, accelerated development timelines. That does not guarantee victory. Fusion is still one of the most complex engineering challenges ever attempted, but momentum has shifted, and the U.S. currently leads in private sector innovation. The next decade will decide everything. Over the next 10 years, we may witness the first net-energy fusion reactor, the first fusion electricity sent to the grid, the birth of an entirely new global industry. Or we may discover that more time and more innovation is needed. But for the first time in history, fusion has moved beyond theory. Real machines are being built. Real companies are racing. Real demand is waiting. In Devons, in Washington State, in California, and soon perhaps in Virginia, small teams of engineers are attempting something extraordinary: to build a star on Earth and use it to power human civilization. If they succeed, the world will enter a new energy era, one that could stabilize grids, reshape economies, and influence life for generations. Fusion will not fix everything, but it may give humanity something rare, a chance to expand what is possible and the power to reach it.